for online reconstruction. So online reconstruction has been there for almost 10 years since the seminal work of Kinect fusion, which was proposed in 2011. That work is kind of like a milestone, and since then, many follow-up works were proposed, and several excellent systems were contributed by the community. And since this dense reconstruction can give a dense representation of the 3D scene in an online manner, many interactive applications can be enabled, such as augmented reality, and also some robotic applications. This is a work from our group. We applied this online reconstruction to enable this robot-operated scene reconstruction. We actually attached a Kinect sensor to the arm of a moving robot. The robot can automatically scan the scene and perform online reconstruction. And the good thing for online reconstruction is that the robot can do some online analysis of the scene, so that she can know where to scan in the next. Basically, we come up with autonomous scene scanning or active vision. And since we have the fine-grained representation of 3D scenes, we can even do some fine-grained interaction between the robot and the scene, such as manipulation or pushing the objects on top of a table. And we also extended this to a multi-robot. We basically mount the RGB-D sensor to each of the robots, and we drive the robots to scan the whole scene simultaneously. And the robots can scan and reconstruct the scene online. And the reconstruction from each robot can be integrated together, so that we have a integrated representation of the scene. We can do the global planning for all the robots to evenly distribute the robots over the whole scene. So there are three key enabling techniques for this online or real-time 3D reconstruction. The first thing is, of course, the sensor, right? It's RGB-D cameras. The most famous one is maybe the Kinect. There is also the Kinect DK, which is the newest model of this series. And the basic techniques, including like the infrared structured light, or TOF. And there's also, of course, SLAM. The technique of SLAM is kind of like to the core of to the center of the online reconstruction. And also there is the depth fusion. This is how the 3D scene is represented and integrated over the time. So volumetric fusion is not a new technique. Even in 2011, when the Kinect fusion was proposed, because it was it can be date back to 1996, which was proposed by Curtis and Levoy. This work is basically represent the 3D scene as a signed distance field. And the good thing is that they only store the SDF around the surface, so that they call this truncated SDF. And in online reconstruction, we basically want to merge this depth map, or we can somehow convert this depth map into a 3D point cloud. And we transform this 3D point cloud into a world reference, so that we can integrate or fuse this 3D point cloud into this TSDF volume. So basically here, the most important thing is that we need to compute an accurate camera pose, so that we can do this fusion more accurately. So here comes the problem of solving the pose of the camera and the map of the environment in simultaneously. So it comes to the problem of SLAM. So SLAM has been well studied for many decades, and there are many excellent methods. Several key problems of SLAM include that the formulation, right? The formulation, how do you optimize how do you formulate an optimization problem for this SLAM? And the other thing is, what is the kinematics modeling? And do you know any prior motion or control motion for this camera? Of course, for like kinetic fusion, the camera is handheld, so maybe probably you don't know any prior kinematics models for this kind of motion. And the other thing is data association problems, and how can you detect and match the features across different frames? And there's also the problem of loop closure. So over these problems, we mainly focus on the first one and the third one. So talking about the first one, the formulation, right? So basically, the formulation stems from the maximization of observation likelihood. We can do a mimic against this structure from motion problem. Basically, reproject a 3D point into different frames so that a reprojection error can be computed between the projections and the detections of the corresponding feature points. And clearly, this is a nonlinear optimization problem against the rotation and the translation. And if you want to solve this nonlinear problem, you need to linearize this objective function so that you can solve it in an iterative manner. And the problem here is that since the nonlinearity is mainly on the rotation, when the rotation is really, really large, I mean, when the motion is very fast and the rotation for each frame is very large in terms of like rotation angle, this nonlinearity of the optimization problem is really high. So that contributes most to the difficulty of this problem. And the other problem is data association, right? So you always need to detect robust features across different frames so that you can do like a feature matching, and you can estimate the pose of the frames, the cameras. And the mainstream methods are all depending on like RGB features, such as shift, orb. There are basically two lines of research. One is feature-based. So you need to detect the key points over some keyframes so that you can maintain or track these features over time. And the other approach is direct SLAM, where you don't need to detect any feature, but still you need to come up some photometric error. Basically, it's a pixel-based error function, right? So no matter which approach you adopt, the method is always depend on the quality of the RGB image, especially when the lighting condition is poor or the motion is really fast. There's always some motion blur in the RGB image. So for this photometric or feature-based SLAM, this is really a big problem. So that's why if you look at all these existing systems for online reconstruction, you will see that the camera motions are really slow, and the operator has to move the robot very carefully so that the camera tracking will not fail. So there are two key challenges for these online RGB-D reconstructions. One is the fast camera motion will cause highly nonlinear optimization. And the other thing is that the fast camera motion will incur motion blur in RGB images. So some people will say, okay, you can use some extra hardware such as inertial measurement unit, which is built in many modern RGB-D sensors. I would say yes, but the problem is that you still have to solve the problem of error accumulation even for IMU, because the drift for IMU is really severe, and you still need to do some synchronization over between the visual sensor and the inertial sensor, and you would also need to solve this some nonlinear optimization problems to estimate the bias of the readings. But so still you have to solve some problems. So we ask a question to us: is there a way to realize fast camera motion online reconstruction without relying on extra hardware? Here's a system that we proposed recently. As you can see that the operator moves the robot really fast, including rolling and swinging of the camera. And the scene can be reconstructed very accurately without any distortion or failure tracking. And here is a live demo of scene scanning. I would say that like for human operator to scan a large scene, if your camera motion has to be very slow and very careful, it's easy for human operators to get bored, because like imagine that you will scan a really large scene, right? So sometimes you just want to go through the scene with some very fast motion, right? Fast camera motion. So here is a very large scene scanned by human, right? As you can see, there are many frames containing severe motion blur in the RGB images. And actually, the camera speed ranges from like 1 meter per second to 3.6 meters per second. And our method can reconstruct the whole scene with correct overall structure. And note that our method does not include any global pose optimization or loop closure. And all the state-of-the-art methods failed to reconstruct this sequence. So here's a sequence coming from the public data set, which is the ETH 3D data set. The sequence is called camera shake. So by the name, you can see that this is a fast motion camera fast camera motion sequence. And if you look at the reconstruction, the live reconstruction demo of these two state-of-the-art methods, boundary fusion and elastic fusion, you will see that, okay, for boundary fusion, many frames were just dropped because of the large error or the tracking failure of those frames. And for elastic fusion, they don't drop any frame, but the tracking is incorrect. And for our method, you can see that we can correctly track the camera motion and reconstruct the scene without dropping any frame. And if you look at the final reconstruction result, you will see that the final reconstruction of our method is actually very complete, and the tracking result is correct. And for boundary fusion, you will see that the overall reconstruction is okay, because they have a processing of a global post optimization, but we don't have that. Our key observation of to solve this problem is that we observe that depth sensors are actually more resilient to motion blur than RGB cameras. This is if you look at the sequence of the RGB and the depths, you will see that when severe motion blur occurs in the RGB images, the depth images are okay. But the only thing is that there will be some missing part around the occlusion boundaries in the depth sensors. This is maybe because that some of the the noisy part around those occlusion boundary were just removed by the depth sensor. But overall, it has a really high frame rate. So the motion blur problem is not a problem for depth sensors. So we have two critical designs. The first one is we want to use random optimization to solve this highly nonlinear problem, since the motion is really big, the rotation is really large. To avoid the optimization get trapped into the local minima, we try to use this random optimization to solve the problem. And the other thing is that since the RGB will be affected severely by the motion blur, we try to solve the problem with some kind of a new objective function, which is defined purely geometrically. Maybe we will define this fitness or objective function based on depth to TSDF conformation. So the second design is okay. It's easy to understand, but for the first one, so it can be a little bit mysterious, because as we all know that random optimization is generally slow, because you need to sample a lot of solutions over the solution space. And so this kind of a method is generally slow. So how can you solve this online reconstruction problem with random optimization? This is the key design of our method. So here, let's take a look at let's have a quick preview of our method. So given a depth image captured by the depth sensor, we can convert this depth image into 3D point cloud. And we can embed this 3D point cloud into the global reference field, the global reference frame, and to put it into the TSDF volume, right? So basically, you will, for each point in the 3D point cloud, it will retrieve a TSDF value over the TSDF volume, right? Okay. Then for each point, you will have a TSDF value, right? So this basically gives you a observation likelihood of your R and T, right? You have a camera pose, you embed this 3D point cloud into the TSDF, and you will compute the observation likelihood of this R and T. So having sampled different R and T, you will have different observation likelihood. And if you want to perform the maximization of the likelihood, you will have this objective function, which is a sum up of the TSDF volume, TSDF values over all the points, right? So then you can continue. So you can always select the best R and T, the rotation and the translation, so that the frame can align well with the surface which has been reconstructed previously, right? So because the TSDF values, the lower the TSDF value, the closer the position is to the surface of the scene, right? So we want to solve this nonlinear problem, optimization problem, with random optimization. We adopt this particle filter optimization, which is a recently studied method for random optimization. So the basic idea is to apply particle filter in solving nonlinear optimization problem. And we sample a set of particles in the solution space, meaning that we sample R and T in the 6D space, and 3D for the rotation and 3D for translation, right? And the key thing is, how do we drive the particles to make them quickly cover the optimal solution in the solution space? Because you sample some particles maybe far away from the optimal solution, so we want to move the particles so that the good solutions will be covered by the particles. So this is the basic idea. So particle filter is write such kind of a method which can drive the particles to cover some good distribution. Particle filter is originally proposed for state estimation, right, based on sequential observations. It uses a set of particles to simulate some kind of a true distribution of possible states. So after some set, we reweight the particles by observation likelihood. So we basically multiply the weight by some kind of observation likelihood, so that those particles with higher observation likelihood will be weighted higher, right? So when we want to apply particle filter to optimization, we regard this state particle as solution, and we regard optimization as the observation as the objectives. So the observation likelihood becomes the fitness of a solution, right? Because we already have that, because we have defined the objective of the optimization problem. So the hope is that after some iterations, regions in the solution space with higher fitness will be populated with more particles or solutions. So the key thing here is where to drive the particles to move, and which particles are probably the good ones. For the likelihood, we already defined the objective function. So this thing is okay. But how to drive the particles? We still need to design some kind of a good dynamic model to drive the particles. But particle filter is time-consuming. The most time-consuming part is the include the particle resampling, particle driving, or particle reweighting, and we basically want to save the computation of these steps. And the other thing is that we want to come up with a smart dynamic model so that we can drive the particles more efficiently towards the optimal solutions. So we have two designs. The first one is to get rid of the particle sampling and resampling. We use a pre-sampled particle set, which is called pre-sampled particle swarm template. We call this particle set a swarm because it's like a swarm, right? It can move and rescale the whole set as a whole over time, so that we don't have to resample, right? We don't have to sample at each iteration. And the other thing is that we come up with a good dynamic model, which is guided by the swarm intelligence. What is swarm intelligence? It is actually very simple. It is just the subset of particles which has a good spot in the solution space. So here's a intuitive illustration of the particle swarm templates. As you can see, we sample some kind of like a sphere in the 6D space. We have all these solutions, right? So for each solution, it is a rigid transformation, right? R and T, and we deform this PST over time. So it deforms from a sphere into some kind of a ellipsoid over time, right? And in each frame, we just deform this this ellipsoid over time, and this ellipsoid will get smaller and smaller, of course, because it converges to some optimal solution over time. And in the next frame, we restart this searching, right? It will, okay. Okay, this is basically a very intuitive explanation of this process. So the thing is that how do we move this the particle? How do you move and rescale this PST, this swarm? It is very simple. We want to use some kind of a particle swarm intelligence. So basically, we identify the particles which has a better solution than the best solution of the previous iteration step, which is called advantage particle set. And over this advantage particle set, we compute the centroid of this subset. And basically, we just move the template or the particles template towards that direction. Okay, this is the moving. So how do you rescale this ellipsoid? The method is that we can, since we have some better solutions towards the direction along the direction of v, this vector, and it is more probable, more likely, better solution will be found along that direction. So that's why we will put more particles along that directions. So we basically deform this ellipsoid to make it along, make it the axis along that direction. So this is the basic idea. And of course, we have some momentum update to keep the update of the ellipsoid stable. And here's the illustration, a visualization of the ellipsoids evolving over time. We can visualize the translation or the axis length by the axis length of this ellipsoid, and the rotation. We can just map the overall rotation or the direction, like over the surface of using the color over the surface of the ellipsoid. So the color distribution basically visualize how the particles orient mostly, right? So here's a visualization of the aligning two frames. Since the two frames have like the geometric arrow is not quite salient, so you will see that the energy landscape is kind of non-convex, right? It is easy to get trapped at local minima, but our method can quickly get to the global minima. And you will see the evolution of the ellipsoid over time. And finally, we'll get a very good alignment for this challenging case. And there are two more challenging cases, and you will see that how the PFO with PST can find the global optimal solution. Here is the probabilistic global model of Rose fusion. Here, I just want to distinguish the PFO from the PF, which has been utilized for many years in the traditional SLAM methods. In traditional particle filter-based SLAM, particle filter was used to estimate the states or the poles of different frames, right? But in our method, the particle filter is utilized in each frame, and it was used to estimate the states or the rotation and or the poles over different iteration steps. So this is the key difference. And we did some GPU implementation of our method we store the TSDF and the PST, all the particles in the GPU, so that we can perform this fitness evaluation of all particles in parallel in the GPU. And in CPU, we simply maintain some global parameters of the PST. And the data transportation between GPU and CPU is minimized. We see that there is no existing RGB-D, no existing data set of RGB-D sequences with fast camera motion. We come up with this kind of this first data set of fast camera motion. The data set is called fast Camo. The fast Camo has two parts. One is synthetic. So the scenes were obtained from the replica data set, and we synthesized some camera trajectories with fast motion, and we render the RGB and depth frames. And we also added some synthetic motion blur for the RGB and the synthetic depth noise to the depth frames. And we also scan some real sequences with Kinect decay. The speed is also, the camera speed is also very, very fast. Since it is a fast motion camera scanning, it is hard to obtain the ground truth trajectory, right? So we basically use some high-end 3D laser scanners to scan the whole scene to do the 3D reconstruction accurately, and we compare the reconstruction quality. So here's an ablation study of our method, which is called like a PFO with PST. PFO means particle filter optimization, and we augmented with a particle swarm template, and we compare it to vanilla PFO and traditional particle swarm optimization. As you can see that our method can converge quickly to the best solution over time and with more certainty. And here is a 2D visualization of the particle evolution in the post estimation of a given frame. And as you can see, our method can quickly converge to some good optimal. And here is the result on a sequence on the data set with ordinary camera speed. This is the ICL data set. This data set is kind of like a slow motion, right? But even for this data set, our method can still achieve a comparable method against the state of the arts. And the key thing, the very critical thing is that our method contains no global post optimization, while like the state of the art methods such as bundle fusion has that. And for the fastest speed sequences of ETH3D, the 3 sequences of camera shake, our method is the only one that can reconstruct all the 3 sequences successfully. And our method contains no global post optimization again. And for this fast Camo dataset synthetic, our method achieves the best over almost all sequences except the room 1 sequence. The room 1 sequence, for this sequence, bundle fusion achieved a very low reconstruction, the tracking error. But the fact is that they dropped some frames, like many frames for this sequence. But well, our method does not drop any frame. And for a fast Camo real, we can only compare the reconstruction completeness and accuracy. And in terms of completeness, our method is the best. And in terms of accuracy, our method is also very competitive compared to the other 2 state-of-the-art methods. And we also compare to this kind of a gradient descent method. Why we compare to this method? Because they use almost the same objective function as ours. And the difference is that they use the gradient descent method, while we use the random optimization method. When tested on the slow motion data set, you will see that their method can converge to almost the same optimal solution as ours, but with maybe a slightly slower speed, convergence speed. But on the fast camera motion sequences, their solution is not as good as ours. And here are some visual results. The red curves are tracked camera trajectories, and the green curves are ground truths. And you can see that our method can follow the ground truth very well, conform to the ground truth very well. And for the bundle fusion, many frames were just dropped. And that's why you will see only the green curves. And these are some real captured data. And you will see that our method can always reconstruct the whole structure correctly. Well, the other two state-of-the-art methods basically fail or cannot reconstruct the whole sequence. And especially I want to mention this, highlight this stairwell, because this sequence is really challenging. There's no salient features, neither in RGB images nor in depth images. There are also some repetitive patterns over the stairs. Our method can still reconstruct the whole thing very accurately. Here is a simulated trajectory captured like a drone flying, right? So we hope that someday our method can be applied to drone navigation or drone obstacle avoidance. Since our method does not rely on images, it of course works in the case where lighting is really bad, right? If you can just turn off the light and our method can still work. And here are some failure cases. The first one is that our method cannot work for the cases where there is no geometric feature at all. For example, this wall is really flat. But in this case, maybe the RGB-based methods can work because there are some posters over the walls. Of course, when the scene contains some transparent objects or the camera motion is really fast, and so that the depth maps are really bad, our method will fail because our method really depends on the quality of depth maps. So as for future works, we want to utilize this random optimization in more problems in SLAM, maybe some loop closure or global pose optimization. And we will also consider how to combine or smoothly transit between photometric and geometric SLAM. And the other thing is that we want to integrate this random optimization with learned priors, which is quite popular in recent. And the other thing is that we can fuse the IMU or multi-model sensory input to so again in the framework of random optimization. So in summary, the key challenges to fast camera motion online reconstruction include high nonlinearity in SLAM and the motion blur caused by the fast camera motion. That's why we come up with this random optimization to address the nonlinearity and the purely geometric fitness to avoid the dependencies on RGB features. So that concludes my talk. I would like to take questions. Thank you for your attention.
Okay, many thanks for Kai's wonderful talk. So in the next, maybe can you turn on the camera?
Oh, I didn't?
Oh, okay. Yeah, you already. Oh, maybe you
I
share
thought
the.
I have already turned on my camera, right?
Okay, good.
Okay,
Okay,
maybe.
okay. So okay, in the next we go to the question and answer session. So in session we also very happy to invite Professor Bailin Deng from Cardiff University and Qixin Huang from UT Austin to join this panel discussion. There are several questions from YouTube and the Games WeChat group. So the first question is that the result is very good. And I wonder that how you get the idea of apply random optimization to solve this traditional optimization problem.
Mhm.
So it means that how you get the idea. Yeah.
It's the motivation is actually quite straightforward because random optimization is known to be very robust against the non-convex objective functions or highly nonlinear objective functions. It is good at getting rid of the local minima. But the problem is that the random optimization is really usually very expensive. That why stops people from doing some research on it. And we just thought that maybe we can do some improvement over this random optimization techniques to make them real time. And here I think the key thing is that the solution space for this kind of a random optimization is not too high because it is only 60, right, for the rotation and the translation. Yeah, so that's why we have this motivation. Yeah.
Okay. So the second question is that for the random optimization, some people maybe have this concern that is it possible that it might fail for some cases? And do you observe this kind of failure case in your experiments? And is there any theoretical guarantee of the algorithm convergence?
Yes, there were some failure cases, such as if there's no geometric feature, meaning that you cannot come up with a good fitness for this kind of case, right? Basically, you cannot tell which pose is really good, which better than all the others, right? And also, our method depends on the depth to TSDF conformation, so that when the depth missing is really severe, and you will not have a good tracking of the cameras. So I think the key thing here is that how do you define your fitness function so that the fitness function will tell a good solution from the others. So talking about the theoretical guarantee, I would say for a random optimization, I'm not sure if there is any the state-of-the-art research on the theoretical guarantee or of the convergence of random optimization. But I would say like random optimization is the strength of random optimization is just to search over a larger solution space in a guided way, right? You can always have a more global solution, but I don't think there is a guarantee maybe. But still, when you have a not bad solution, or maybe you find some good solution in the solution space, you can still perform some fine-grained tuning of the solution, maybe using some gradient descent method.
Okay, thank you. Okay, and the following question is that notice that the DI fusion has performed online implicit 3D reconstruction with deeper pairs. Is it possible to combine random optimization and deeper pairs into an online 3D fusion framework?
Yes.
I think we can mention that in the future work.
Right. Yes. I would say it's quite possible, especially that I just mentioned one thing, which is the dynamic model of the update of the particles, right, in the particle filter. That means that you need to have some good priors or some good guidance of the particles. I would say these kind of priors can be learned from data. So that you will drive the particles or move the solutions more smartly, so that you can get the optimal solution more efficiently. So I would say this is a good combination point. Yeah.
Okay. So Dani and Qixing, do you have some questions to the talk?
So maybe I can start asking one question, and we can iterate. So Kevin, this is a wonderful talk, wonderful work.
Thank you.
Right. So in terms of the motion blur, right? So in the vision community, right? So people started this kind of event-based sensors, right? So I think the event-based sensors not there yet, but at least theoretically, it has this kind of very high dynamic range, very high frequency, right? So that can address the motion blur, right? So, but of course, it's not a 3D sensor. It has to be synchronized with what you have, right? But I was wondering, what is your perspective on this, right? In terms of the future plans.
Yes. Thank you, Peter, for this excellent question. Yes, I would say event camera is really a good option for this online reconstruction with fast camera motion, because it has a really high frame rate or dynamic range. I would say it's a very promising direction. We actually had tried some. We did some initial preliminary test on this. The main difficulty we encountered was that the synchronization between the camera, the event camera and the visual camera is not easy, because it seems that the resolution of the event camera is not very high, so that we cannot. It is not easy to perform accurate synchronization or calibration of the two. But still, I would say as the progressing of this event camera, I would say at some point there will be some a good point to combine the two. So I would say this is a good direction. Yeah.
Okay. So I leave this to Balin to ask the next question.
Thank you. Yeah, thank you, Kevin, for the excellent talk and excellent work. So I have a question about the use of color information in this process. So I think right now this is a purely geometrical based method. Yes. So you basically discard all the information from the photo. But my understanding is that you can somehow quite robustly reconstruct the relative translation and rotation between two frames. So if we have this information, would it be possible to use this information to help us deblur the blur RGB frame that you've got, and then use that to further improve the result?
Yeah. Yes, this is a very interesting idea, and since you can have a good tracking, and you can use this motion to some kind of do some kind of a recovery of the motion blurred image, and once you have some recovered details, maybe you can even use the details to enhance the geometry of the 3D reconstruction. I would say this is a interesting idea, and there is already some works that utilizing the shadings from the RGB images to enhance the depth images, right? So I would say this is a very good point, especially talking about the depth images. As I mentioned that in the beginning of this talk, under the fast motion, there will be some missing area around the the occlusion boundaries in the depth images. So once you have, you can maybe recover the fine details in the RGB images. You can maybe add the details back by doing some shape from shading or something. I think this is a very good point. Yeah, thank you for pointing to this.
Thank you.
So Jixin and Balin, do you have any other question for the talk? Okay, if not, so we will go to the next the panel discussion stage. We have some open questions from the audience, and we wanted to get some comments from all of you three guys. So the first question is that I think so one of you maybe already noticed that recently 3D reconstruction from multi-view image or just molecular RGB video sequence will already achieve a very promising result with the help of differentiable volumetric rendering like software rationalization or LoRF. And some related work like IDR from Yazong Lippmann and news from Wenping Wang. And it seems that we can also achieve very good 3D reconstruction result without depth information. So can you share some thoughts on this aspect? Okay, maybe Kai, you go first.
Okay. Yes, I think that this is there's already some works like proposing like a neural representation of the 3D scenes as a storage of the 3D scene in replace of the TSDF volumes, which is really the memory consumption is really high, right? So I think this is an interesting direction. But in terms of depth images, I would say since the commodity depth sensors are ubiquitous, it is quite cheap to acquire some depth images or depth sequences. I do not see the need or the necessity of avoiding any depth images and use the pure RGB images. I would say maybe the combination of the two. You can use some depth sequences to do some very rough or maybe some low-res reconstruction, and then you can have the learned priors to enhance your reconstruction with more details. These are some ideas or comments from myself. Yeah, maybe Peter and Balin can have more comments.
Okay, so maybe I can chime in so to share some thoughts. So I fully agree with Kevin, right? So I think we should not really say that we should combine, right? So I think every this kind of information resource, right? So it's useful to some extent, right? So the question here is how to combine them together, right? So I think we already discussed that it's difficult to synchronize the events cameras with another camera, right? Whenever they are not really manufactured to be synchronized together. For example, I think the advances in neural representations could be helpful as a data representation to do this kind of what Kevin talked about, right? So when we get the scans, right, maybe some deep priors can be used to denoise, right, to complete some missing holes, right? So those are the things that are very difficult, right, to ensure that the scanned geometry, right, we cover every single pixel, right? So those can be addressed by some deep priors, right, using some advances in neural shape representations, right? In particular, I think there's some recent works on this kind of open, right? So implicit surfaces with boundaries, right? So that would be very helpful for this kind of scans. I also Kevin mentioned in the talk, for example, in no lighting conditions, right, in the evening, right. So this is also a huge issue in autonomous driving, right? In no light conditions, we cannot rely on this kind of standard image cameras because those are dark, right? So and also in fast motions, the video cameras output are very actually blurry, right? If you think about the multi-view image reconstructions, the input images should have high quality, right? So if you have motion blurs in the input images, then and the correspondence problem becomes tricky, right? So, but I still want to say that I think the advances there can be incorporated, right? It's just like it's challenging, okay, to synchronize everything together. Okay, but we still have to solve the post problem, right? It's optimization problem, right? So in this kind of online construction, right? So those problems are shared. Okay. Yeah.
Yeah. Okay. Thank you.
I also fully agree with Kevin and Peter on the possibility of combining color information and depth to try to get a better result. I think Kevin's work showed that even if you only use depth alone, you can get pretty good results. And the other works like nerve and other color-based reconstruction, it shows that if you go to the other direction, to the extreme, you can also get pretty good results purely based on color. So it would be very interesting to see whether it's possible to take advantage of both of them and to get even better reconstruction results. So I think right now it looks like, for example, Peter mentioned about the issues of not fully synchronized input from color and depth. Maybe if there's a need for such a multimodal reconstruction, maybe in the future, the hardware can be further developed to maybe incorporate both color and depth, and maybe even with some incorporated chips for neural acceleration to get even better reconstruction results. So maybe in the future we can see such a package that can synchronize color and depth and also do reconstruction in real time. Maybe that's a possibility.
Okay, thank you. Okay, the second question is from the Kevin's talk, we can see that random optimization achieve very good result for this challenging nonlinear optimization problem. And we can see that there are also a lot of nonlinear optimization problem in traditional computer graphics, like physics-based simulation or optimize the distortion, the mapping of from 3D to 2D. And so, okay, a very straightforward idea is just extend this random optimization to solve this kind of other problem like parameterization. So, so if yes, so if you think is it possible to extend this random optimization to this optimization problem? If yes, there is. Do we need to some kind of problems to solve this the other problems? Okay. No, can you hear me?
Yeah. Right. So if you want to use a random optimization for any kind of optimization problem, I think that there are two design guidelines. Is that the solution space cannot be really high because you always want to sample some solutions from the space. If you get a very high dimensional space, you will the efficiency will be a problem. And the other thing is that you can evaluate the fitness of the solutions very efficiently. In our case, the dimensionality is x6, so it's not very high. And the other thing is that the fitness of the solutions can be evaluated very efficiently because it's just embed the point cloud into the TSDF and do the queries of the TSDF values. So this part can be very fast in especially implemented with GPU. Yeah.
Yeah.
So I can share some thoughts on this. I fully agree with Kevin, right? So number one, I think the dimension cannot be very high, but I also have some personal experience that even in 6 dimension, right? So the problem is actually not easy, right? So in particular, if you have a geometry, the shape, right? In particular for things we have very characterized environments, there are actually a lot of local minimas, okay? Without this kind of sampling, right? So to address those, it could be very challenging. Even in 60, right? Even we have like some reasonable initial guess, okay, but still there are a lot of local minimas, okay. So I think what Kevin presented in the talk is actually a very good progress along this direction, right? So but for other problems, right, in computer graphics, we have high dimensional search space, okay, as in physical simulation. I think the problems over there a lot more challenging. One potential approach is to think about, right, so maybe we can do some dimension reduction, right, doing some dimension reduction, right, so to reduce the search space from very high dimension, okay, to some low dimensional space, but not 0, okay, not 1, okay, 2, 3, 6, or 7. Then that opens the space to apply what Kevin mentioned. Okay, so I think to extend it to very high dimensional space, we need some to combine different approaches. Okay, so that is my thought. Okay, on this. Yeah.
Yeah, I agree with Peter and Kevin that if you directly apply this approach to high-dimensional problems, it probably will be too slow. So I think Peter's suggestion on using dimensionality reduction would be a very good one. So probably you can find out some specific problem-specific approach to reduce the dimensionality according to some priors in your problem, and maybe that would be good enough to get a reasonably good result. And also, I think for high dimensional problem, basically any sort of global optimization would be difficult. So potentially this sort of dimensionality reduction can be combined with other sorts of global optimization approach to benefit from the guarantee of getting a better global result. So I think possibly not only just the random optimization approach can be used here, and maybe other global optimization can be combined with dimensionality reduction and help us to improve the result as well.
Okay, thank you. So actually, I have one more related question is that so in Kevin's work, so national is many focused on this rigid registration, that it just have 6 freedoms. But I mean, after kernel fusion, we also have this dynamic fusion. So it like the moving object or like a human body. So is it possible to extend this random optimization from rigid object to non-rigid object?
Yeah, this is an interesting question. Yeah, we did think about this, like tracking the human motions in fast motion, right? The problem is that like the human motion is can be very high degree of freedom. So it is really hard. Maybe intermediate problem is that you can address the problem with some of the objects in the scene are rigidly moving, right? You can still track the camera and disambiguate the motion of the objects and the motion of the camera. I think this is a more solvable problem in the current framework. Because maybe Peter has more experience on like a human body tracking. Maybe you can have more comments.
I can share some thoughts on this. I agree with Kevin. I think this so in this kind of cluttered environment, people like the human subjects are moving, and then we want to reconstruct the detailed geometry. I think so the common state of the art, what I can see is that we try to, for them, detect the key points of the humans, detect the moving skeleton, then maybe feed a SMPM model to that, right? So that is what I think right now can be achieved under limited sensory inputs. If we really want to solve the geometry reconstruction problem by building correspondences, solving non-visual deformation, because a lot of occlusions, right? A lot of occlusions, and it's difficult. Okay, I think the correspondence problem is very challenging. Okay, correspondence problem is very challenging. I think it's not easy to beat. So there are a lot of papers in the vision community, right? So they use this kind of SMPM model, right? So the very very strong prior, okay, to do shape reconstruction. So most of the signals from of the reconstruction come from those kind of deep priors. But if we really want to solve the reconstruction problem, it's difficult. It's difficult. Okay. I think we need to have better representations of humans, right? The better representations of the priors. What kind of priors we can narrate? Right, the motion priors is very important. So I think that part is still open problem. Okay, it's still open problem, right? We are trying to, if we do not utilize any priors, human shape priors, motion priors, and we want to reconstruct dynamic objects, okay, directly from the sensory inputs, I think it's still very challenging. Okay, we have so that is my sense. Okay, but of course there's if we use priors, of course, like how about the humans with cloth, right? How about the humans are interacting with objects, right? So how about this kind of fingers, right? Gestures. So those are like emotions, right? So I think those are very difficult to reconstruct. Okay. We are not there yet. Okay, but
okay.
Yeah. So that is my sense.
Okay. Qixi and Banning, do you have any other questions? Maybe we can have this panel discussion.
I do have one question to answer for Kevin, is that, so basically right now you focus on this kind of basically indoor environment, right? Indoor environment, right? So at least the evaluation part. How would you approach like study this kind of outdoor environment, very large scale, even like very large scale buildings, right? So this kind of museums. Would you want to go like scale up in terms of size, right? Of the geometry. So do you consider those extensions?
Yeah, this is the interesting direction. So talking about outdoor environments, I think the main challenges there is how do you handle like the really large scene representation, right? You have to represent the large scene more efficiently. But for outdoor scenes, I think maybe like the drone application will be relevant. And if you how can you reconstruct the scene with a drone, because drone can fly really fast. But there you will have to resolve the problem of have a efficient representation of the scene, so that you can do this kind of objective function, define this objective function or fitness. For indoor scene, maybe for outdoor scene, you need to use other kind of sensors, right? You cannot use depth sensors or RGB-D sensors. You will use some kind of a so the most mainstream methods are based on monocular or binocular RGB images, but some of them maybe use LiDAR. So you will need to have a very brand new design for those kind of sensors. Yeah. So Peter, so what do you expect to maybe the
so
main
I think
challenges?
outdoor could be quite I think a lot more challenging than the indoor. So I personally worked on this like a couple years ago, right? So I started working on the outdoor data sets on the Google Street View, but eventually I worked on indoor version. Okay, because indoor I think the data is cleaner. Outdoor we have all kinds of challenges. Okay, and with them outdoor, I think there are certain places we cannot reach. Okay, like certain camera poses, right? So drone maybe resolve this, but for example, if we are acquiring the city, right, and using a car, then it's challenging. Okay, it's very challenging. The data, right? The data is limited. Okay, so I think outdoor is very difficult. I do agree with that, John. In particular, how to do the view planning, right? Combining view planning and with I think the drone has all kinds of issues, right? So this kind of motion blur, very fast motion, right?
Right.
I think there are a lot of challenges over there. Yeah. So I do see that there's another field there, for example, in vision, or maybe in computational photography, where we try to do some kind of this kind of deep blurring, right? So we have some blurs. We do some deep blurring. Maybe those kind of like deep blurred images could be very helpful. Okay.
Yes.
Yeah. So I think it's an exciting space. There are a lot of challenges. Okay. Another thing that we have discussed is that was like the multimodal, right? So multimodal fusion is very important. Okay. But there are a lot of challenges over there. Yeah.
Yes.
Okay. So Balin, do you have other questions?
No, I think Peter summarized the question pretty well.
Okay, yeah, maybe the time is we need the time is okay. We're already 1 hour and 15. So maybe we need to conclude the talk here. So let's thanks for Kai's wonderful talk and also Peter and Balin's comments and inspiring discussions. Okay, so maybe so in next week we will continue next Wednesday and see you next week. Thank you all for your attention and bye bye.
Thank you. Bye bye.
Okay. Thank you. Bye bye.
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 Thank you.
Thank you. Okay. Bye.
Bye bye.
Bye.
Okay.
Bye.